giving me the opportunity to talk today. And so what I would like to present is some work on the quantum local charges in some certain QFTs, which are called chiral affine Gaudin models, which essentially will be conformal field theories based on current algebras, as we would say. And so this is based on some slightly older work already by Benoit Bicedo and Charles Young, but also on some more recent work with Lev Kutuzov and Jörg Teschner, in which we got more additional results and also some new perspectives on the questions. So I'll be talking about Gaudin models, and Gaudin models in general are certain physical systems which are associated with Lie algebras, and they've been studied a lot for the case where the Lie algebras is finite dimensional, in which case it essentially takes the form of a system of interacting spins with a finite number of degrees of freedom. And that, for instance, we've heard about these type of models in the talks of Volker and Jeremy 2 days ago. And so for this talk, what I want to discuss is the case of affine Gaudin models, which correspond to the case where the underlying Lie algebra is an affine Lie algebra, which in particular is infinite dimension. And so there will be infinitely many degrees of freedom in the theory, and actually they will package into some fields. So we'll get a field theory which will be built in terms of a certain number of fields called Kac-Moody current, which will satisfy certain commutation relation essentially corresponding to these affine Lie algebra. And so at the classical level, where essentially now we have Poisson brackets instead of commutation, then we know that this theory is classically integrable in the sense that we can build an infinite family of Poisson commuting charges from this Kac-Moody current, which can be built either in a local or in a non-local way from the current. But at the quantum level, the integrability is still conjectural, and that's one of the questions that I want to address in the talk. And so the approach that I will follow is the following. So the idea is that a natural starting point to look for quantization is to look at what I will call chiral AGMs, which is the case where all the Kac-Moody currents are, let's say, left-moving fields of a 2D CFT. But they could be also all right-moving fields, but I focus then essentially on a chiral half of a certain conformal field theory. And then I can quantize this using the standard language of 2D CFT, and what I get is a certain current vertex operator algebra. And so, as we can see, essentially what we're looking at is the chiral half of a certain two-dimensional CFT based on currents. And actually, as we will see, we will have more generally coset of current algebras. And so in this talk, what I would like to present is some first results and conjectures about quantum integrable structures in such models, and more precisely then the construction and the diagonalization of quantum local charges inside of this algebra. And let me just mention, so this, essentially the idea then is that I look at the conformal points of this model and look at the chiral integral structure in the chiral half, which then goes into the general program of studying integrable structure of conformal field theory, which has been pioneered in the work of Bajanov, Lukyanov, and Zamolodchikov, and which have been studied a lot since then, including by people in the audience. And so we can see what I will present as part of these kind of general ideas. And finally, let me mention that in terms of motivations, these ideas of affine Gaudin models can be applied, for instance, to the study of integrable stigma model, and for instance, the quantization at conformal points. And that we've heard a bit about this in the talk of Jörg Teschner earlier. And so for this talk, I will actually not focus at all on the sigma model applications. I will really focus on the affine Gaudin model and how we build charges in this sphere. And so my plan will actually be extremely simple. I will start by defining a affine Gaudin model at the classical level, and there I will explain how we build charges that Poisson commutes. And then I will describe their quantization, and here, well, things will be a bit more complicated. I will present some first results and some conjectures on how we quantize the charges before concluding. So let me start with classical affine Gaudin model. So the data defining such a model is the choice of a simple, complex, finite dimensional Lie algebra, and then a certain number of continuous parameters. So n of them I'll call the punctures. They're just endpoints in the complex plane, which I think will all these things. And then n to each of these punctures I'll associate a certain level, which here is a number Lr, which I suppose is a non-zero complex number. And let me just mention here, I take everything to be complexified. In the end, of course, to get physical model, we should impose some reality condition. But here I mostly want to have algebraic work, so I can complexify everything and work with the complexified algebra and parameters. And to fix the convention of the algebra, I take TA to be a basis, so I can define a structure constants FABC by the commutation relation. And I take eta AB to be an invariant bilinear form. Essentially, it's the Killing form, just normalized in some specific way, which I call minimal. The details do not really matter. And because my algebra is simple, then it means it's non-degenerate, so I can define its inverse, which I denote by raising the indices. And as usual, I can use eta to lower and raise indices in my Lie algebra. And I have all the ingredients to define the fundamental fields of my affine Gaudin model, which are called Kac-Moody currents. So there's n of them attached to the n punctures, so they're labeled by r, which is from 1 to n, and they're fields in the sense that they depend on a space variable, x, which here I'll take from 0 to 2 pi, and I'll suppose periodic boundary conditions. And these fields are valued in the Lie algebra, and their main property is that they have a certain Poisson bracket, which, to describe it, so I decompose the field into the basis TA, so I get the components, and I get the following Poisson bracket for the components. So what I see is that in front here I have a Kronecker delta in RNS, so that means that Kac-Moody current which are associated to different punctures, the Poisson commute, they're independent. And then I get some structure FABC, JC, which look like the commutation relation, but I have also a Dirac distribution of the space variable, which we expect in an Hamiltonian field theory. And finally, there's the central extension term with the derivative of the Dirac distribution, and which is proportional to this level. So these parts of the parameter here, the level, they enter the definition of the Poisson structure of the model. Now, key ingredients in the definition of the Gaudin model are the so-called Gaudin-Lax matrix and twist functions, which are a function of the spectral parameter Z, which is an auxiliary complex parameter. And so they have poles exactly at this choice of punctures ZR, and the corresponding residue of the Gaudin-Lax matrix gamma is the Kac-Moody current, and then for the twist function phi Z, the residue is the corresponding level. So now the twist function is just a certain rational function which includes all the parameters of the theory, the punctures and the levels, and also I have access to all the fields of my theory packaged into this Gaudin-Lax matrix. In particular, because I know the Poisson bracket of the Kac-Moody current, I can compute the Poisson bracket of this gamma, and in the end I find this rather simple formula, which in particular has the nice property that it's independent of the number of punctures and the position of the punctures. We repackaged everything in terms of the spectral parameter dependence. And so this, for us, will be a key formula because it will allow us to compute a lot of Poisson brackets inside of our Gaudin, of our model. In particular, what I would like to explain now is how, starting from this key formula, we can build a lot of objects that, in fact, Poisson commutes. So some of these objects will be non-local charges, and they will be built by the standard formalism of Lax matrices in field theories. And here the Lax matrix is defined almost as this Gaudin-Lax matrix gamma. I just need to divide by the twist function, which is independent of the field. And then because I know the Poisson bracket of gamma with itself, then I can compute the Poisson bracket of L with itself. And here I won't go into the detail because it will not really matter for us, but it takes the form which is a very specific form called the Maillet bracket with a non-skew symmetric R matrix satisfying the classical Yang-Baxter equation. The point being that this Maillet bracket ensures that we can build an infinite number of non-local charges in involution, looking at the monodromy of this Lax matrix. So I take its half-ordered exponential on the cycle, and then the result is that from the Maillet bracket, one shows that traces of this monodromy in different representation at different values of the spectral parameter all Poisson commute. So we get then an infinitely many conserved charges that commute by Taylor expanding in Z as we usually do. But so let me stress that these charges are in general quite non-local because they're built from this half-ordered exponential. But in addition to these non-local charges, turn out to be also some local charges which are built in an independent way and which will be the main protagonist of this tool. And so I will describe their construction in more details a bit after, but just to say a bit what they essentially depend on. So they are labeled by two indices I and P. I goes from 1 to n minus 1 is essentially, as we will see, it will be associated with the zeros of the twist function. For some reason I will explain. So essentially, the more punctures I have, the more of these i's I will have. And then for each fixed I, so for each fixed 0, I will have an infinite hierarchy of local charges, which will be labeled by this index P, which is an infinite set of integers, which essentially will describe the degree of this charge in a certain sense. And well, the main property of this charge is that they will be all Poisson commuting one way or another. And moreover, they also Poisson commute with the charges, non-local charges built from the monodromy, but it turned out that they're actually not contained in these charges. They're independent sets somehow. And well, to be able to construct them, so I need to use the zeros of the twist function. So very quickly, we introduce the twist function with the following expression here in terms of our punctures and levels. So of course I can put this in the same denominator. I get a degree n-1 polynomial, which I can put in factorized form. And then instead of thinking of the theory described instead of the set of parameters ZR, LR, I can also describe it by the position of the punctures, position of the zeros, and then I need a global factor K, and it will be slightly easier for us to think of this set of parameters. And now all the charges, they're built in the following way. So they're local in the sense that they're the integral on the space variable, dx, of a local density. And this local density, well, the way it's built is we start with our Gaudin Lax matrix gamma. We take p+1 of its component, which we contract with a certain symmetric tensor of degree p+1 on our Lie algebra. And then, so that's almost the thing that we put into the charge, but actually what we will have to do is we'll have to evaluate it at the zeros of the twist function, and so that's why they will be associated to these zeros, and I will explain why we need to do that a bit later. So now the main new ingredient that we had as these symmetric tensors, and these, we cannot take them to be any symmetric tensors. We have to have some algebraic conditions on them. So first of all, they should be invariant to the commutation relations. And also they should satisfy some property when you contract two of these tensors together, they should have some natural property. I won't go into the details of all this, but the main thing is that in the end, these properties, they're chosen so that you get a simple form for the Poisson bracket of two densities together. And well, this type of Poisson bracket, it can be computed from our key formula that we had for the Poisson of gamma. And so in the end, what we'll have is two types of term, one proportional to delta, one proportional to derivative of delta. Recall that all of this is to build local charges in the end, so I will integrate over the space variable. So if I focus on a term, for instance, with the derivative of delta, once I integrate over x, this will not contribute. So I can actually forget about this. Then I get a contribution from delta, and similarly, if I have a space derivative with respect to y there, it will not contribute. And then the magic here is that the specific choice of symmetric tensor is such that the remaining term, well, they're non-zero, but they're proportional to the twist functions phi z and phi w. Which means then quite obviously that if I take now the evaluation at the zeros of the twist function, then I get something that commutes, which in the end exactly ensures why all these charges Poisson commute one over another. Here let me actually mention that this is somehow slightly different than the standard law of integrability, let's say, where we would have a generating functions that would Poisson commute for all values of the spatial parameter, and then we would expand in Z to get infinite number. Here we actually have to make the evaluation at finite numbers of specific points in the complex parameter plane, but we still get an infinite number because we have an infinite number of generating functions. Some said we vary the degree.
So, and how do you see locality here? That was the claim, they are local.
They're local because really in the end the density is really just a certain polynomial in my Kac-Moody current. So they're local as the densities are local combinations of my Kac-Moody currents.
Localized in many points.
Sorry?
Localized in many different points.
No, so they're all evaluated at the same point x, right? So if I look at one charge, it's the integral of a dx of a certain polynomial of my fields, but all evaluated at the same point x. So this is really a local composite field, right? Built of a certain number of Kac-Moody current components, which I contract in a certain specific way. But importantly, it's not something where I have, like, let's say, two integral over dx1, dx2 of something in x1 times something in x2. It's really all local in that sense.
I have a question about these points where are you, the punctures. So it seems like the number of puncture is related to the number of degrees of freedom. Because
essentially, yeah.
So what are they? Because can you give an example, specific example, what the punctures will be for some specific theory?
Yes. So for instance, if we take the example of the one simple example would be the principal chiral model, where in that case, essentially what we will have is we'll have one puncture, but it will turn out to be a second order puncture. There's a generalization where instead of having simple pole, we have double order pole, which essentially is equivalent to having, it looks like having two simple pole and then we make them collide. So that, like a typical example, like a PCM, let's say, would be something where you have two currents in there, typically. So that's part of the simplest case. And then we can go to quite higher number of punctures, and that in the language of sigma models will correspond to actually coupled models on n copies of a group that interact in some way, and the way they interact is related to the position of these poles, essentially. Okay, so, well, now the main thing that I have to use for this construction are these invariant tensors, so I won't really explain how they're built, but just to give a few informations about them. It turns out that they were found already earlier in a paper of Evans, Hassan, McKay, and Montaigne, which actually exactly looked at local charges in evolution in the case of the principal Gaudin model. And that corresponds to a very specific example of affine Gaudin model, but these tensors, they can be used then more generally. And so they're labeled by this P, and P belongs to actually known sets of integers, which are called the affine exponents of the Lie algebra. So they always depend on the choice of Lie algebra, but they always start with P equal 1, which means that we'll start with a certain tensor of degree 2, so a quadratic tensor, and in that case, it's nothing but an odd choice of being an invariant Killing form, essentially. But then we can have higher degree 1, cubic, quartic, and so on, depending on the Lie algebra. And to give a slightly more concrete example, if I take G to be SLK, then in that case, the exponents turn out to be all the integers except the multiple of K. I keep all the multiples of K. And then the first tensors, they look like that. So the quadratic one, it's the billionaire form, which for SLK is essentially the billionaire trace in our fundamental representation. Then the cubic one is the cubic trace symmetrized in indices. But the first interesting thing happens for the quartic one, where we take the quartic trace symmetrized, but that actually would not satisfy the good property to have Poisson brackets commuting. We actually need to correct it by something squared in the billionaire trace with some very specific prefactor which is fine-tuned so that in the end we get the right property. And then for a higher degree, there's some kind of algorithm to generate them, some kind of generating function, where we'll get more and more of these kind of lower corrections with some very fine-tuned parameters so that everything works. Okay. So another important property of these densities is their Poisson bracket not between themselves, but with an object that I'll call the diagonal current, which is just the sum of all my currents here. And what we find is that actually this Poisson bracket is also proportional to the twist function. So when I take the evaluation at a 0 of the twist function, of course, I get something that Poisson commute, meaning that actually my local densities, they're invariant to certain symmetries. So they're invariant to the symmetry generated, the canonical symmetry generated by this diagonal current, which are called the diagonal gauge symmetry. Here I speak of a gauge symmetry because importantly, we commute not only with the integral of the current, but really with the current itself, so at all values of y, so we get a local symmetry. And if you do the computation, you find it takes this form, so it depends on the gauge parameter h, which is valued in a group associated to the Lie algebra. And then essentially what we see is that the Kac-Moody current, they behave as gauge field under this. So they transform by adjoint action plus the derivative term that depend on the levels. But what's important also is that we act simultaneously on all the Kac-Moody currents. So that's why I called it diagonal. And then under this specific transformation, the densities will be invariant. And actually, we can show that the non-local charges will also be invariant with the same symmetry. And we can reformulate this by saying that these densities, they actually belong to what I call the classical coset W algebra, which is simply defined as, well, I take differential polynomials in my Kac-Moody current components, and I ask that they're gauge invariant so that they have 0 Poisson bracket with the diagonal current. And that form a certain coset W algebra, which is then essentially the coset of n copies of the affine algebra, which are my n Kac-Moody current, and I quotient by the diagonal action, which correspond to this gauge symmetry. In particular, an important element in this W algebra, which turned out we can always get it from the quadratic densities by taking a good linear combination. It takes the following form here, so it's built from our current in a way, and what we see is that it takes the form of sum of TR minus TDiag, where TR is this object, and some of you might recognize here the energy momentum tensor of a Kac-Moody current through the Segal-Sugawara construction, so the classical Segal-Sugawara construction. And so what we do is we take the sum of all this for all the currents, so we have the total energy momentum tensor, and then we remove the diagonal part, and that's what we call the GKO coset construction, which is how we build the energy momentum tensor of the coset, right? So this element will commute with JDiag, and it generates the X diffeomorphism inside of my W algebra, and then it satisfies the classical Virasoro algebra, which take this form in terms of Poisson brackets. Okay, so that was mainly what I wanted to say for the classical space. Let me just check now I'm in time. Yeah. And so now, in the second part, I would like to go quantum. And so to go quantum, what I'll do is I'll start by supposing that I have a chiral affine Gaudin model, which, as I said, is essentially, I suppose that my currents, they're all left-moving fields of a 2D CFT, or maybe right-moving. So I'm working in a chiral half of a current CFT, essentially. And then we know that these quantize as current VOAs, which concretely mean that now I have some quantum Cox-Moody current, which I'll denote by this straight J here, and which satisfy the following commutation relation, which are just the quantization of our Poisson bracket. And well, to make this even more explicit, so the classical limit will go as follows. The quantum current will look like the classical one over h bar with some prefactors. Similarly, the kr, they're the quantum numbers, and they go like the classical one over h bar. And then if you put this back inside of the commutation relation, you see that indeed this commutator takes the form of ih bar Poisson bracket plus I order correction. And well, actually the reason I put this 2 pi here is kind of conventional. It's in the end to make one other thing simpler, which is the operator product expansion. So we know that here in the DCFT, we can encode actually the commutation relation inside of the operator product expansion of 2 of these fields, and then the short distance divergences will essentially encode our commutation relation. So for instance, the first order pole will correspond to the delta term here, and the second order pole to the central extension. And now I'll typically think of OP instead of commutation relations. Now, well, what we can do in particular is we can look at this diagonal symmetry that we had at the classical case. There should be an equivalent of that in the quantum case. So we can define the quantum diagonal current, and we can define the quantum coset W algebra, which is essentially the same construction as before, but quantum. So I take differential polynomials in my Cox-Moody current. Now, because it's quantum, I need to take care of ordering, so I normal order everything. And then I ask that they have regular OP with the diagonal current, which essentially mean that there will be then gauge invariant. And so that defined for me my quantum coset W algebra, which is in particular closed under OP, and which form the algebra of extended conformal symmetry of my model, in a sense that it described the algebra of local physical, so gauge invariant, left-moving fields of my theory, for instance. And now I can, well, get to, first one particular nice element of this W algebra is once again the energy momentum tensor, which is built by the GKO coset construction, which is essentially what I had before. There's just now the quantum version, so now I need to normal order my fields. And also the levels now get shifted, it get a quantum correction, which is a shift by the so-called dual Coxeter number, which is quite known from 2D CFT. Essentially, the definition is if I take this partial combination, this is the Killing form, so it should be proportional to my billionaire form. And actually, the factor of proportionalization is just this 2h check. But we can just think of it as being a certain integer associated to Lie algebra, which we know from tables. So for SLK, it's k, for instance. And this then satisfies the Virasoro OPs as general. We have now a central extension term, the central charge, which we can explicitly compute in terms of the dimension of G and of the levels. And just to be very explicit, if I expand this T of x in Fourier modes, introducing this mode Ln here, I have a shift in the 0 mode by C over 24 because we work on the cycle. And then the OP translate to some commutator for the modes, which is just the standard Virasoro algebra in modes. And now I can get, well, to the main question here, which is, well, can I get quantum integrability in there? Can I construct an infinite family of local charges whose density would be certain element of the W algebra, which would all commute one with another, and which would be a quantization of these local classical charges I presented before. So for that, I will give a very brief reminder of classical local charges. I won't re-explain everything. I just want to recall one particular property, which is that in the end, the things that makes it work is that in our Poisson bracket, we made things proportional to the twist function appeared. And so then we could take the evaluation of the zeros, and then we got terms that cancel, and we get commutation from there. And now one can wonder if we can do the same thing at the quantum level, and well, little spoiler, we can't. We will have to make some kind of quantum corrections to this. And so the question is, well, what will be the quantum equivalence of these two conditions, 1 and 2? And so to explain that, well, a key role was played by the twist function in the Gaudin X matrix. So I can look at their corresponding quantum version, which are defined as follow, which look like the classical one over h bar, essentially, with some prefactor. And well, in particular, I can look at the OP of two of these Gaudin X matrix, which is the quantum version of what I called the key formula before, which was the Poisson bracket of Gaudin, right? And it essentially takes the exact same form as before, it's just a quantum OP now, instead of a Poisson bracket. And now from there, I can use it to compute a lot of OPs, so a lot of commutation relation. And to start to study this question of the local charges that commute, I can look at the first step, which would be the quadratic charge. And here I take the quantum quadratic density essentially as in the classical case, just I normal order my two components here. And I can look at the OP of two of these densities. And when I find the following expression where I have poles that go from 1 to 4, now well, the pole from 2 to 4, they will correspond in a commutator to derivative of the Dirac distribution. So this, it will not contribute once I take the integral over the space variable in my local charges. So I can focus on the other one pole, A0, and what I find is the following. So I get a spatial derivative, which then I can also forget. And then I have what I will call twisted derivative, which are defined as follows. So when it acts on a function f, it's the derivative with respect to the spectral parameter, shifted by essentially the multiplication by the quantum twist function with some prefactors. And here let me briefly observe that, well, recall that in the classical limit, the quantum twist function behaves as the classical 1 over h bar. So in particular, this term here will behave as 1 over h bar. Well, this term actually does not diverge. So actually this term here will be subdominant in the classical limit. And what we see is that in the classical limit, this essentially will correspond to having something proportional to the twist function. So that's why we recover what we had in the classical case, where the Poisson bracket had term proportional to the twist function. But now what we see is that we have some kind of quantum corrections to that, which takes the form of this twisted derivative. And I can look also similarly at the OP of the quadratic density with the diagonal current. And once again, I find that instead of something proportional to the twist function, I get a twisted derivative of something. So now I cannot apply the exact same recipe as before of evaluating at the zeros of the twist function to get things that commute. I need to find another way of building gauge invariant commuting charges from there. And here, that's what I would like to explain. And here, a key role will be played by this multi-valued function pz, which is defined as follows from the punctures and the levels. And essentially, the way to understand this definition is just such that he satisfied this differential equation. So essentially, its logarithmic derivative is the quantum twist function. And this has a nice property with the twisted derivative, which is that if I take such a twisted derivative, multiply it by an appropriate power of p, then this turns out to be just a total derivative with respect to z. And that I just can see from the Leibniz property and then this expression for the derivative of z, I will exactly recreate this term here by the Leibniz rule if you do the computation. And so the consequence of that is that, well, if I take this quantity, because it's a total z derivative, if I integrate it over a closed cycle, then I will get the variation at the initial point minus the variation at the final point, which is the same, so I should get 0. Actually, that does not work exactly like that. There's a small subtlety which will be important, which is that pz in general is multi-valued. So when I go through a closed contour, in general, I could pick up a monodromy, and so it's not true actually that my initial point will cancel with the final point. So what I need to do for this to be true is I need to choose very specific contours, which are called Pochhammer contours, which are closed contour in a complex plane, where essentially along them I can define a single valued branch for pz. So that's maybe a bit abstract, so just to give an example, if I take two punctures here, I can build one of these Pochhammer contour in the following way. I start around ZR, I goes around it, so I pick up a monodromy. I go around the other puncture, I take another monodromy, and then I go around ZR again, but this time in the other direction. So now I pick up the inverse monodromy, and essentially in the end I cancel everything. Once I do it, when I come back, actually all my monodromies cancel, and I really have a single valued branch for pz there. And for these contours, then this property here for the Pochhammer integrals will be true. And now that's exactly what I will use to construct my local charges that commute. So the local charges in the sense that they're integral of a certain spatial density. And now the spatial density, that's what's new in the quantum level, they're defined as these kind of Pochhammer integrals. And the reason we do that is recall, for instance, that the OP of the quadratic density with the diagonal current is given by a certain twisted derivative. And we know that integrals, Pochhammer integrals of twisted derivative are 0. So essentially, by this definition, I ensure that here I get a regular OP. So this is gauge invariant. It's in the W algebra. And similarly, if I look at the OP of S2 with S2, remember that essentially what we got as just spatial derivative plus twisted derivative. So once I do the integral both on space and both Pochhammer integral on the spectral parameter, I get objects that commute for all of these different Pochhammer contours. So that's typically how we get these local charges that commute in this model. And well, just to mention here something, the apparition of these Pochhammer integrals, some of you might recognize here some results, something that looks like some results of Lukyanov and Bajanov-Lukyanov in the study of the ODI QFT correspondence for the Fateev integrable structure. And well, I will actually talk again about these 2 points a bit more later, but here I just wanted to mention that actually this idea, that the appearance of these Pochhammer integrals in his work was part of the motivation for the introduction and the study of these twisted derivative and Pochhammer integrals. So, of course, this was all quadratic, so one can wonder about a higher degree charge, because in the end we really want an infinite number of these. And well, here there's a very natural conjecture to make from what we have, is that for every exponent p, there will exist a certain density of spin p plus 1, which is built, well, there's a term that looks like the classical one. We take the same tensor as before, and we contract the quantum Gaudin matrix now normal ordered. And actually, this won't be enough in general. We would have to add also some quantum corrections, which essentially are built from a lower number of these gamma, very fine-tuned, but also derivative of gamma, both with respect to z or x. And these quantum corrections, they should be exactly such that the OP of two densities essentially have spatial derivative plus twisted derivative, and once again, the OP diagonal current is just twisted derivative. And then, of course, everything that I explained before works again for these charges, and so we get infinite. If we have this conjecture, then the consequence will be we have infinitely many commuting charges with gauge invariant densities, which are built as these Pochhammer integrals.
How do you define the normal ordering?
So here, by normal ordering, what I will actually mean is the first regular term in the OP, essentially.
But you have more than just two operators.
Then we do it. I mean, from the left to the right, right? Okay. So as I said, this is a conjecture. So let me maybe say what is the status currently of the conjecture. So essentially, what I presented before for the quadratic was the proof of the conjecture for the quadratic density, and that works for any Lie algebra. Then I can ask for the cubic, which would be the next step. So these actually turns out to not exist for any Lie algebra. You should only take SLK when k is bigger than 2. And then in this paper here, we actually built the explicit density and showed that it satisfied a good conjecture. Then you can look at SL2, and you can then here you skip the cubic, but then the next one would be quartic. And here the density, we built it in our last paper with Lepkotusov and Teschner. And well, the details don't really matter, but I give here the expression just for having a little flavor of what's happening. And essentially what we see is that we indeed get this term which looks like the classical term, and then we get a whole bunch of quantum correction, which are built from lower number of gamma and their derivative. The details don't really matter, but what we see is that we need to have very specific prefactors in all of that. And all of these need to be very fine-tuned so that in the end the conjecture works.
Can you relate the tensors and the other factors back to your invariant tensors?
So you mean this tensor T3 or?
No, the other one, the structure constant.
Well, the other ones, I mean, of course what we know is, essentially, we know always that the tensor from which we're going to build these we're going to always be invariant tensors. So essentially we'll build everything from lower degree invariant tensors. Which one up here actually is not so obvious. Because for instance, initially we had something where we had only symmetric tensors. But now what we see is that, for instance, FABC starts to appear, which is not symmetric. And I think the reason is that classically, we essentially build everything from this first term, which have no derivative. So essentially, we can always symmetrize the tensor. But once you start having terms which also involve derivatives of gamma, then in some sense you're building things from different fields. So you cannot always assume symmetry, and then other terms can appear. And in general, you could have very complicated tensors that could appear. And here, well, this gives us just a flavor of basically that the more we go in degree, the more non-trivial correction we'd have. So probably a like brute force approach is maybe not the best one, but well, let me just mention still that you could always take a set and ansatz, put this in a computer, and then with enough computer power and time, you could in the end solve the conditions. But still, it will grow more and more difficult.
Actually, your definition of normal ordering was not symmetric.
True. That's also true. Yes. So now, one thing that I would like to mention is actually, we could ask what's the relation with the classical construction? Because in the classical construction, we have this evaluation at the zeros. How is that related to these Pochhammer integrals that we're doing? And for that, well, we can take our density defined as a Pochhammer contour and look at the classical limit. And so remember that the quantum Gaudin-Lax matrix, it behaves as the classical 1 over h bar. So if I look at my density here, well, this term will behave as 1 over h bar to the power p plus 1. And then the other correction term, because they're built from lower number of gamma, then they will be subdominant in the limit. So inside of my integral here, the density part will essentially look like the classical S plus iota corrections. And I can look also at the limit of this pz. Here I'll skip the details, but essentially the fact that d log of pz is the twist function, and then the twist function looks like the classical 1 over h bar. What we get in the end is some term like that behaves as an exponential of 1 over h bar times a function rho, which have the property that its derivative is the classical twist function. And now we want to take the limit h bar of this, and that we actually know how to do it. We can use the saddle point method. And the saddle point method exactly tells us that the integral localizes at the extrema of this function rho z, and because rho prime is the twist function, then these extrema are nothing but the zeros of the twist function. And so that's how we recover the classical construction. By the saddle point approximation, in the limit, our quantum densities will essentially yield linear combinations of our classical densities evaluated at the zeros. And then what we see is that in the Poisson bracket that becomes OP, our terms proportional to the twist function becomes twisted derivative, and similarly, evaluation at the zeros of the twist function become Pochhammer integrals. Okay, so now, well, so far I focused mostly on the construction of these local charges and the fact that they commute, but we can also ask about the spectrum, right? Because I have a bunch of Kac-Moody current, I can take representations of these Kac-Moody currents, so representation of g hat to the n, and then these are now operators. My charges will be operator commuting, acting on this particular Hilbert space, and I can ask about their common eigenvectors and common eigenvalues. And here, unfortunately, I don't have the time to go in more detail, but let me briefly mention that there's an idea that quantization of Carl AGM should be related to some conjectured affine version of the Langlands geometric correspondence, which essentially tells us some information, some conjectures about the spectrum of the affine Gaudin models. And what it tells us is that the spectrum of these charges should be encoded in some objects called affine pairs. And then a conjecture by Fagan and Frenkel is that this actually turns out to be essentially the same thing as the ODE IQFT correspondence, which have been studied in many papers, including by people in the audience. And in particular here I mentioned some of the results of Lukyanov and Bajanov-Lukyanov, where they realized that in some models the eigenvalues of the local charges could be expressed as certain Pochhammer integrals. And that actually is quite reminiscent of the construction of the charges for us. And also from studying this idea of affine Langlands correspondence, we add in some more general cases also some results that indicate that indeed these eigenvalues could be in general themselves Pochhammer integrals. So I don't have the time to go in all details here, but if you want, I'm happy to talk about this later. And let me also mention that all this was a bit abstract, but there's one case where we can be also quite concrete, which is the case where we act on the highest weight representation of the affine Lie algebra. So now we have a reference state, and we can essentially do some algebraic Bethe-ansatz there. Once again, I don't have the time to go in details, but actually what we get in the end are rather precise results and conjectures for the eigenvectors and the eigenvalues of these charges. In particular, for instance, a closed expression for the eigenvectors, which would work for any Lie algebra, any number of punctures, any number of Bethe excitation, and that actually is also not nested, it's direct expression. And some conjectures also on the eigenvalues here. Now, final thing that I would like to say is to actually give a more concrete example of all this thing by specifying a bit more the setup, and which will turn out to be the Fatiev integrable structure, of which we've also heard before, for instance, in Gleb's talk, and more precisely the conformal point of this Fatiev integrable structure. So to do that, what we do is we take only two punctures, so n equal 2, and we take the Lie algebra to be SL2. So now essentially what we're looking at is this type of coset CFT here. And in particular, we can apply this all AGM machinery and construct local charges that commute. And that's what we did in the paper with Gleb Kutuzov and Job Teschner. And we looked at the first one, so the quadratic one and the quartic one. And so essentially what that means here is we need to perform these Pochhammer integrals. And so here I won't explain all this in details, but the idea is that we have only two punctures, so we can always fix them to 0 and 1. And actually, I always put this under the rug, but I always have one at infinity that I kind of don't touch. And then these Pochhammer integrals, they essentially take the form of integral representation for the Euler beta functions, which I can compute very explicitly, and it satisfies also a bunch of recursion relation, which I can use to, in the end, compute very explicitly the densities. And for instance, for the quadratic one, I find this thing up to a factor, which is just the GKO energy momentum tensor. And one of the reasons I mentioned that is actually what we see is that this shift by +2, where here 2 is just the Coxeter number, dual Coxeter number of SL2. In this construction, we see them appearing from these Pochhammer integrals. So classically, we would not have them, but the fact that at the quantum level we do this Pochhammer integral is essentially how we will recover this kind of shift, which are quite well known in the CFT language. And then we did also build the quartic one. I won't show it because it's quite ugly, but we have a very explicit expression. And in particular, from there, we did some various comparisons with other works in the literature. So, for instance, we showed that these two charges, they agree with what is called a screening charge computation, where essentially we look at a free field realization of the W algebra, and we build the charges as the commutant with some screening charge, and these were studied in various papers, including, for instance, Fagin, Semikhatov, and Lukyanov, Samadchikov. We have some checks concerning the non-local charges as well, but that I don't really have time to enter into the details. And finally, we have some very preliminary checks concerning the ODE-IQFT correspondence, essentially checking that we get the same type of ODEs from these affine opera construction in Gaudin, and some ODEs that were studied in works, for instance, of Bajanov and Lukyanov for the Fatiev model in particular. And so that's essentially what I wanted to explain, so let me then go to the conclusion. So essentially, to summarize you, what I did is present some first results and conjectures on the study of quantum local charges in chiral AGMs, so the construction and the diagonalization. Of course, the most natural perspective here is to go to full proof of this. Well, as we saw, having a very brute force approach to the question is probably quite difficult because we got more and more corrections. But one hope is maybe to have a proof in the spirit of a certain paper of Fagin, Frenkel, Reshetikhin, where they looked at the quantum integral structure of finite Gaudin model. And the idea would be to try to do an affine version of this. And what this actually would put us, the hint here would be to look at certain double affine algebra, where essentially one affine direction will be the affine direction I already have, so the space dimension. And then the other affine direction would be the spectral parameter. And then we would work in this kind of big algebra upstairs and hopefully get some results about, in the end, this construction. Of course, this is very vague at the moment, and this is long perspective. Also, I focused here quite a lot on local charges, but we can ask about non-local ones, which were in the monodromy. Here, the main obstacle for quantization is the so-called problem of non-neutral locality, which essentially prevents the naive use of the standard techniques like the quantum inverse scattering method. But let me mention that here also there's quite a lot of results, some first results and conjecture that have been found in various papers. And let me particularly mention this paper of Bajanov, Kutuzov, Lukyanov, where essentially in the example of the Fatiev model, they show several hints that actually if there is the problem of non-neutral locality, there should be a quantum monodromy that satisfies a quantum RTT relation with a Yang-Maxwell algebra, so there should be still a quantum inverse scattering method in some form, even though there's the problem of non-neutral locality, which is quite interesting because this is a quite long-standing problem. Also, let me mention that, well, this construction of Gaudin that allows to recover various type of integrable hierarchies. So here, for instance, I gave the example of FATF, but you can also, at least expectingly, because of course we don't have the full construction, so these are conjectures, but there's some, it seems that we could recover, for instance, the KDV integrable structure, also the Drinfeld-Sokolov, which is essentially higher rank KDV, and these could have application in various type of things, but also, for instance, in sigma models. Just to mention a few idea of perspective, so there's various ways that we could generalize this thing. I actually mentioned it earlier for the PCM, but so we could consider higher order poles, where at the punctures, instead of having simple poles in gamma and phi, we have higher order. And then in practice, what it means is that instead of considering Kex-Moody currents, we should consider what I call Takif currents, which have also been studied in the context of 2D CFTs. We could look at what I call cyclotomic model, which are the case where there's some equivalence property with respect to automorphism of the Lie algebra, which, for instance, would lead to other type of coset models. And then mention that for all these things, at the classical level, everything is very well understood, but at the quantum level, there's still a lot to explore. There's various relations to other type of, to other subjects. Here I just give some keywords just to mention them. So of course there's the ODI QFT correspondence, which for us was quite a big motivation for all of these. But outside of that, there's also a relation to toroidal algebras and the affine Youngians, and also some relations to what is called the semi-topological 4D Chern-Simons theory. And finally, let me mention that all this also, one of the motivation, as I said, was the application to integrable sigma models and the quantization at their conformal points. And that we've heard about it in Teschner's talk, but there's still a lot of things to explore also in these directions. And also finally, the last comment is, of course, all this was focusing on the conformal model. The hope would be that maybe we could even go massive by kind of recombining the left-moving and right-moving chiralities, but this is quite, of course, quite a long-term perspective. But hopefully maybe we can have something, and here, for instance, the results existing on, let's say, the massive deformation of the ODI QFT that we've heard, for instance, also in the talk of Gleb, are a very good indication that hopefully there is actually a non-trivial structure in all this. And with that, I end my presentation.